Our world constantly relies on mathematical technology to operate. But when did we first begin to build the foundations of our mathematics? When many of us think of the origins of mathematics, the first thing that comes to mind is ancient Greece. But several artifacts from diverse parts of the world show that advanced mathematics were being explored more than 1,000 years before Pythagoras. In particular, we'll meet a cuneiform tablet known as Plimpton 322, found in the desert of Iraq around 1920. Along the way, we'll travel around New York City and meet a cast of scholars as we trace the journey of Plimpton 322 and how its significance eventually came to light. We'll also explore other artifacts that reveal the ancient origins of our mathematics. My name is Laurence Kirby, and I'm a professor of mathematics at Baruch College in New York City. This is the story of Plimpton 322. We're about to witness an ancient ritual, a token of a 5,000-year cultural inheritance. And here it comes. The people going about their business or pleasure here take it for granted, but sometimes we get excited about it. So how did 12 get to be at the top and mark new beginnings? And why do we count our minutes and seconds by 60s? These two numbers will take us on the trail of a much wider tradition that's central to the ways we make our society, all this, work. In 2008, the British Museum sent a delegation to inspect important archaeological sites in Iraq. One of them was Tel Senkere. It wasn't safe to stay long, even with their military escort. They found a guard tower with bullet holes, but no guards. 4,000 years ago, this was the city of Larsa, and it was the Sumerians who lived here then who gave us the 60s that still measure our time. And here in Larsa, sometime around 1920, a small piece of clay was dug out of the ground. This cuneiform tablet would eventually come to be known as Plimpton 322.
Mathematics and science didn't begin 2,500 years ago in the Eastern Mediterranean, but 5,000 years ago in the Persian and Arabic Gulf.
Right.
And that's actually quite a dramatic realignment of our mental chronologies that we have to make. You know, we just have to double the length of history.
The dissemination of an idea in the ancient world, how long and torturous it was. I mean, for it to gain local acceptance, for it to move within a locality, for it to move geographically across continents, plural, and the dangers it was fraught with.
It starts off in the sort of southern Iraqi end as a basic means of feeding families. You know, you dig up tablets like you might harvest crops, and you sell them on like you would go and take your food to market. At a time when Iraq had been part of the Ottoman Empire, the very eastern end of it, and on the border with Persia, what was later to become Iran. And although the Ottoman authorities had formal antiquities laws, they were very difficult to police and put in practice in what was then desert, very, very far away.
1917, the British Army enters Baghdad and starts to mould this corner of the crumbling Ottoman Empire into the new nation of Iraq.
Western museums and Western collectors were very interested in Babylonian material because of their biblical collections in particular. And the region was very poor, and so therefore there developed quite a sophisticated market in antiquities excavated directly from the ground in order to feed the antiquities dealers in Baghdad and Paris and London, and then there are various itinerant antiquities dealers in the States, in particular a man called Edgar Banks.
Edgar J. Banks, the first American to cross the Arabian desert by camel and the model for Indiana Jones. In his travels he visited Larsa, where he said that
a slave called me aside to a clump of bushes to show me a human skeleton which had been gnawed bare by the jackals, and then he pointed to his gun. He was the owner of the gun. I killed him last summer, he said.
Banks resigned as an archaeologist under suspicion of stealing antiquities. After a brief stint in Hollywood, he sold ancient tablets to supplement his main livelihood of growing oranges.
But he very much traded on this idea of tablets as evidence for the biblical past.
Our mathematical debt to the Sumerians goes far beyond those 60s. We've come uptown to Columbia University to see firsthand the breadth of this inheritance. This is the home of Plimpton 322.
George Arthur Plimpton and his dear friend David Eugene Smith gave both of their collections to Columbia. Even as early as 1904, he was trying to acquire Babylonian clay tablets to round out or to bring his collection to an earlier era. He was interested in collecting anything that he could get his hands on in printed and manuscript form having to do with the history of education. He being a publisher of textbooks. The so-called Plimpton 322, numbered because there are about 500 tablets here at Columbia. This one happened to be given the number 322, came in 1923. He purchased it along with 4 other tablets for $10 from Edgar J. Banks.
Let's look at some of the other tablets in George Plimpton's collection before asking why number 322 is so special. Here, we're close to the origins of our arithmetic. The calculations are in base 60. So this is a geometry problem, and it's literally a scratch pad. Underneath, if you're an expert, you can see the scratchings out of earlier calculations of the student who tried to figure out a problem familiar from the middle grades, which is the area of a trapezoid.
Mostly they weren't intended to survive. That's ephemera. It's a little scrap that should have been scrunched up and reused, but it just happens to come down to us. So it's a really very precious object.
A powerful Sumerian advance was positional number notation. We still use it. The meaning of a symbol depends on its position, so that with only a finite set of symbols we can write any number, no matter how large, and break up a problem into simple steps which are uniform. You follow exactly the same rules for each column. And once you know this procedure, this algorithm, you can deal with fractions in exactly the same way, with the aid of one new symbol, our decimal point.
Positional notation are absolutely fundamental for doing any form of sophisticated calculation. And it just so happens that they use positional notation in base 60, and because there was no other equivalently functional effective system in the ancient world even 2,000 years later, that when the Greeks started to get interested in astronomical calculation, they adopted the Babylonian system, and that's why we have still 60 minutes in an hour and 60 seconds in a minute, and we divide the circle into 60s and 360s.
Most of the mathematical tablets here at Columbia University are accounts. Account of animal hides, account of fodder.
What's very interesting, actually, we can say that the basic use of writing even was for accounting. It's been estimated, I think quite accurately, that about 97% of the written documents from about 4,000 years ago in southern Iraq are primarily account keeping. That writing and counting and calculating were all for keeping track of assets and debts and property.
Some of the world's earliest spreadsheets, invented by some anonymous Sumerian scribe. Information in table form, instantly updatable, at least while the clay's fresh. One man did more than anyone else to awaken the world to the ancient Mesopotamian roots of our mathematics. He was Otto Neugebauer, an Austrian mathematician at the University of Göttingen in Germany.
When the Nazi government came in 1933, and the Jewish and other racially unacceptable members of faculty were fired, Neugebauer was asked if he would take over as the director. He refused. He would not sign the papers, and within a few months he had left for Denmark, where he was able to continue working at a distance with the community of mathematicians and historians of mathematics. By 1939, that had become already pretty risky. It was pretty clear that Germany was going to be invading countries like Denmark soon. And in America, he was wanted not just as a historian, but because he knew how to run a journal for reviewing mathematical work.
So in 1939, Neugebauer sailed into New York Harbor aboard the MS Batory to take up his new position at Brown University. He would soon encounter Plimpton 322, working with an American Assyriologist, Abraham Sachs.
Plimpton dies in 1936, and in 1943, Isaac Mendelssohn prepared this catalog of the Babylonian tablets here at Columbia. And in this very helpful catalog, which brought to the attention of the world what was here, he actually interprets the item 322 as a commercial account. However, there was also, thanks to photography, a photograph of the item itself. And it was that Otto Neugebauer was able to interpret in 1945.
But for a long time it languished in the collection here, not particularly regarded.
Well, until Neugebauer and Sachs published their work.
And what they said was, this column and this column on each row are two members of what we call a Pythagorean triple. Those two columns begin like this, using modern numerals. Here's the hidden pattern that Neugebauer spotted. Each row can be grown into an example of Pythagoras' famous theorem using whole numbers. Three whole numbers that work like this are called a Pythagorean triple. The scribe who found and arranged them so cunningly at about the same time that the patriarch Abraham was growing up in the nearby city of Ur had a deep knowledge of the phenomenon we call the Pythagorean theorem. It was surprising to the world of 1945, which was accustomed to thinking of mathematics as a Greek invention, to find the sophisticated calculations on here.
Dating 1,000 years prior.
Prior to Pythagoras.
Yes.
So you need the gloved hands to handle this. So the scribe, or the teacher, as Ellen Robson suggests, that made this, drew those lines starting the same columns off. And it looks as if he intended to continue the process on the other side.
Right. But a serious break has been repaired here, as it shows on the back.
We've known about this tablet since 1945, when Neugebauer and Sachs published their edition of it. And what's going on in it is apparently so much more complicated than you find even in the more advanced other Babylonian tablets, and hard to situate in the context of what the problem texts in general are doing, that the scholars who have specialized in studying Babylonian mathematics have never been able to come to an agreement about what it was for, how it was made, and what's the missing part of it, because it looks like a complete tablet, but actually there's about a third of it or so that's missing on the left-hand side. What it's for, what it really meant to the person who wrote this tablet, remains hotly debated.
It looked much more like mathematics than the rest of Babylonian mathematics did to a mid-20th century mathematical audience. It was something they could relate to very closely. And I found in my own experiences of presenting this material that many mathematicians with an amateur interest in history have failed to realize that there were words on the tablet at all, and have taken it as a purely numerical table and have constructed all sorts of elaborate mathematical fantasies around the numbers.
There's lots we could have known about Plimpton 322, but don't, because like so many of these objects, it was unscientifically excavated, so that we know nothing of their all-important context. War makes the problem worse.
The recent estimates are that about 10% of the surface of archaeological sites in Iraq have been destroyed through looting since 2003. And that is an extraordinary loss of data that is irrecoverable forever. That archaeology itself is a destructive process, but it's a controlled one. Looting, unimaginable amounts of evidence are lost forever to future generations, and that's just incalculably sad.
It's precisely the context, the social meaning of an object that interests modern scholars. What kind of society produced it? Who wrote it?
Each state was essentially independent with a small hinterland around it that could support it. And every now and again, very powerful and charismatic leaders would come up and gobble up neighbouring cities as well and create larger territorial units, but they never held for more than a generation or two. Communication systems and technologies were not effective enough to support large territorial states at this point in history. That really it's a bit like medieval Europe, where you've got lots of tiny little principalities, all in constantly changing alliances and states of war. So southern Iraq, Babylonia 4,000 years ago was like that. We think now of southern Iraq as being completely desert, but the two great rivers, the Tigris and the Euphrates, run through it, and at the time many canals running off it, a very fertile, rich plain, so very like sort of the big farming plains of North America or Europe, highly irrigated, but then needing a lot of management. We don't know exactly who wrote Plimpton 322, but we know quite a lot about the sorts of people who might have written it. So we can say some very basic things like they were probably male, certainly living in a city and not a farmer or a nomad. They were professionally trained in literacy and numeracy, so that, therefore, a scribe, that tablet in particular, is about creating a set of numbers that can be used in school exercises.
When the students got to a more advanced level, they were doing a lot of problem solving. And the problem solving is almost always expressed in terms of real world situations that they would encounter when they went on to their professional lives, usually running projects like building walls or building containers for storage of grain, or trenches or dikes to keep the river flooding from going over the croplands. So here we have a tablet that's full of problems without the answers that have to do with digging a trench, probably for a canal.
The training then to become a bureaucrat or a manager or administrator involves very fundamentally becoming numerate and learning also far more about mathematical skills than you would actually need. And a lot of it is, like Plimpton 322, is beyond the everyday needs of those accounts. It's not simply accounting. It's learning the abstract principles of calculating and measuring fairly, that there's a big emphasis on social justice, that the king's rhetoric and royal inscriptions is all about being fair and ensuring that, as they say, the strong don't oppress the weak and the rich don't exploit the poor.
So this is a student working out what sounds like a fairly simple problem. How to find the area of a field of land that's shaped like a square and you know the length of the side of the square. What makes it a bit harder is that this is using the ancient Babylonian units of measure, and they don't work out nicely like areas with sides in feet come out in square feet. The unit of area is not based on the square of the unit of length. The problem and its answer are written neatly in the lower right-hand corner. The calculation in base 60 is done in the upper left-hand corner. This is what's called a hand tablet. It's a little tablet just shaped the right size for holding in your hand and writing with the stylus. Very typical for student work.
Not all scholars are so sure how or even whether the ancient mathematics came down to us.
We know very little about routes of transmission or even about how much did get transmitted out of Mesopotamia into neighboring cultures. We find things that are mathematically related in Egypt, not very much later than these old Babylonian tablets. And then much later, when we get into classical antiquity, the time of the Greeks and Romans, you find Greek mathematicians doing things that are not so close, but still mathematically cousins, you might say, of the problems that you find in Babylonian texts. But this is more than 1,000 years later, and there seem to be very great differences too. We really don't know whether the Greeks owed their knowledge of some of these fundamental things to much more ancient Babylonians through unknown routes of transmission, or did they rediscover them? We may never know the answer to these questions.
In the cloisters of the Metropolitan Museum in New York, there hangs a magnificent tapestry which tells the tale of the unicorn. At the end, we see the miraculous animal captured, gracefully resigned to his fate, standing in an enclosure surrounded by a neat little fence. This picture may serve as a simile for what we have attempted here. We have artfully erected from small bits of evidence the fence, inside which we hope to have enclosed what may appear as a possible living creature. Reality, however, may be vastly different from the product of our imagination. Perhaps it is vain to hope for anything more than a picture which is pleasing to the constructive mind when we try to restore the past.
All over the world, people are putting 12 at the top. Why is that? Well, that takes us back to Africa, the far north of Africa, Egypt in fact, where a high official of the 18th dynasty by the name of Senmut designed his own tomb. And on that tomb, he used 12 divisions of the night and 12 divisions of the day, and they became our hours. If Plimpton 322 is our most celebrated evidence for the reach of ancient Babylonian mathematics, its Egyptian counterpart is the Rhind papyrus, named for Sir Henry Rhind, who bought it in Luxor in 1858. Most of that papyrus is now in the British Museum in London, but I've heard that a fragment of it made its way to New York City, here to the Brooklyn Museum. So I hurried across the river to see what I can learn about ancient Egyptian mathematics.
The Rhind papyrus is believed to date from the Second Intermediate period, about 1650 or so BCE. The scribe Ahmes, who wrote the Rhind mathematical papyrus, also indicates that it wasn't all his creation, but rather that this text is a copy of a much earlier text, and that earlier original, which unfortunately we don't have or don't know the whereabouts of, dates to the 12th dynasty, so over a century before the Rhind mathematical papyrus.
So these fragments of a wide-ranging work on arithmetic and geometry are roughly contemporary with Plimpton 322. We also went into the vaults to see an Egyptian measuring rod, but it's made of stone, not exactly practical for everyday use, so it's intended as a votive offering.
Each digit, as was each number for the ancient Egyptians, considered to be, in a sense, sacred, and each digit was associated with a specific deity, and this particular cubit actually mentions the temple of Amun-Re, so although I don't know for sure, it may have been offered to the temple of Amun-Re.
Re is the sun god?
Yes.
Looks like a sun.
Absolutely, Re is the sun god, and he's followed by the god Shu, who's represented with an ostrich feather, and he's the god of air.
In fact, many of the greatest Greek mathematicians, including the most famous of all, Euclid, lived and worked in Alexandria. And Alexandria is in Egypt.
In Egypt, yes, that's right. It's this fantastic hybrid place where the scholars speak Greek. It's actually part of the Roman Empire. It's still very Egyptian as well. It's an amazing hybrid of many, many cultures. And the remit of the library founded in Alexander's name was just to collect the world's knowledge together.
Sometimes what isn't there can tell you a lot. There's a non-barking dog on Plimpton 322, a tiny blank space. It turns out that's a position where we would put a zero. This absence is the first step on the long road to our sleek, modern, multifunction number 0. Along the centuries, 0 was refined and extended in China and India. No doubt the merchants along the Great Silk Road found it useful and spread the idea. In fact, we can trace the origins of all our modern 10 digits to India. The Chinese made a bizarre and beautiful discovery, the negative numbers. It was a long time before they were accepted as real, but today negative numbers in Wall Street can have very real effects on all of us. East and West came together in the new capital city of the Abbasid Caliphs, Baghdad. Yes, our journeys brought us back to Iraq.
The Caliph Mamun had a dream, it has been recorded, where he dreamt of the Greek philosopher Aristotle, who came to him in a dream and said, there is no inherent contradiction between reasoned thought and religion, which was a concept that was reassuring to him and also inspirational, because from that point on he sent his scholars, emissaries, to all parts of the ancient world, especially to Constantinople, to try to bring back as much of the Greek learning that had survived and was still lying dormant in those parts of the world, back to the House of Wisdom in 9th century Baghdad. From about 800 until almost 1300, for about 500 years, while Europe was languishing and festering in their dark Middle Ages, where learning didn't exist, no new ideas were hatched, and much was destroyed. During that period, Baghdad was the world center of education and culture. It was the largest city in the world, and scholars came from all over, so that Copts from Alexandria, Egypt, and Hindus from universities in the East would come and mingle in the streets of Baghdad. People from all religions, and even in the same religion, they were coming from different parts of the world. Muslims from India were completely different than Muslims from the Mideast. They had different traditions they brought with them. And Muslims from North Africa, they were different. And they were bringing all those different cultural traditions together. And yet they got along. And they learned from each other. At the end of that first 100 years, there was a great librarian there by the name of Al-Khwarizmi, who is called today the father of algebra, for no other reason than his book, Kitab al-Jabra, which means putting together or reuniting, has given the name to the word algebra.
Besides algebra, Al-Khwarizmi gave the 21st century another crucial word. From his name we get the word algorithm. An algorithm's just a set of instructions for manipulating data. Since we learned how to embody algorithms on microchips, this has truly been the age of the algorithm. Every time we use a digital device, it's running on algorithms. What makes Wall Street tick? Algorithms. I had a chance to look at a book on algebra by a man who wrote his poetry in Persian, but his mathematics in Arabic, the language of learning at that time.
This volume has a text of Omar Khayyam, along with about 14 other Arabic manuscript texts.
But this volume is also important because it contains translations into Arabic of the ancient Greek mathematicians Archimedes and Apollonius. And we see that nexus, transmission of knowledge from the Greek through the Arabic to the Latin.
There was a great school of translators in Toledo, and that's really where most of the classic works got translated from the Arabic finally into Latin, which then became the sparks of the Renaissance.
Witness the first ever translation of the fundamental work of Euclid into Latin, the language of learning of Europe. It's by an English monk named Adelard, a contemporary of Omar Khayyam. And the importance of this is that apparently he translated Euclid not from the original Greek into Latin, but from the Arabic into Latin. Caliph al-Mamun of Baghdad was a practical man, and he valued results, and these methods of Al-Khwarizmi and the other mathematicians of the House of Wisdom gave results, and it was that appealed to the bankers in Florence in the Renaissance of Europe, and they imported his methods. Of course, the ultimate origin of human mathematics must take us back to Africa, but we have scant evidence. This is the Virunga National Park in the Democratic Republic of the Congo, the last refuge of the endangered mountain gorilla and buffeted by, once again, war and civil strife, so that the park rangers carry guns. From here came the Ishango bone, now thought to be more than 20,000 years old. Are those carefully carved notches for counting something? Is there a hidden mathematical pattern in the arrangement? Or are they merely decoration? Another thing we'll never know. Africa, Asia, the Middle East, Europe, all the fruitful diversity of ancient Baghdad or Alexandria come together in the mathematics that drives the 21st century. And just as each of us honors this heritage whenever we use a clock or an algorithm, each of us needs the power of this knowledge. If you have an opportunity to learn some mathematics, make the most of it. To succeed, as those old Babylonian students knew, means hard work and practice, but it's worth it.
I know people that are in the floor covering business that use the same equation today, so maybe back then they were doing the same thing as well.
You think of math and you definitely don't think of old ancient tablets with calculations on them, so it was quite an eye-opener when I was able to go to the exhibition and see all of these old tablets from Mesopotamia.
Babylonian numbers and the columns made it look like a ancient version of Excel spreadsheet. So, and it had like a machine-like quality to it.
It is too bad that Mr. Plimpton couldn't actually get to see the importance of this little piece of clay. It looks like a little piece of clay, but there was so much history in there.